I'm Tasfahun Alamo. Today, in this video, I will show you how to analyze factorial RCBD design with two factors. This can be extrapolated for other three factors or four factors. So usually RCBD factorial or factorial RCBD is used in order to study two-factor combinations and to understand how the level of each factor interact each other in order to affect the response variable of the treatment. So usually this design or factorial arrangement is used for agronomic studies with a small number of factor level combinations, and sometimes also with the forage for livestock research groups, especially for forage research, and also even some animal digestibility study like that. So in order to do this analysis, first is you should set as a working directory. This one will help you in order to easily access the data and also try to save the output data directly. So to set your working directory, you can do in two ways. One way is by using the function called setwd, and then you can provide directly the path of your working directory. But the easiest one is, I think you can go here on the file side. You go to your where your folder is in your file. So when you go here, for example, in my case, my data is found in the desktops. So I'll go for the desktop, and then I found unrecorded video, and then finally I will come here in more, and then I will set as a working directory. So the next step is to load the function you want to use, the package you are going to use. In this case, for example, you can load library agricoli. And the next one is you should read the data you want to analyze. So in our case here, factorial RCBD .csv is our data. So directly what you're gonna do is I'll use the read csv function, and then I will touch tab. So he'll give me an option to select which one of my data of interest to be analyzed. So in this case, factorial RCBD data is my interest. So then I will run it. So now here, if you see it, we found 27 observation and 6 variables. Data is read. And then it is better to do is to see the summary of the data. So here's the summary of the data. It will help you how much observation, and sometimes if you have this numeric data, it will show you the minimum, the maximum, and the median, and the mean, so that it will show you how, if your data is in the right range, or if it is something have some problem, you can correct it before further analysis. So the next step is you should change the two-factor variables. So in our case, there are three factors. The first factor is the block. The second factor is the nitrogen, and the third factor is the irrigation. So I should change these two factor. So using the function as factor, simply you can change it. Then when you check the structure here, you will see that if the variables are changed to factor accordingly, you will show like this: block, nitrogen, and irrigation. So another wise, usually when you have factorial analysis, there is an expected that it will have some interaction effect. So sometimes it is possible to visualize using the interaction plot function. So in this case, for example, if you see this one, the first one, for example, is it helps you to order your factor level as low, medium, and high in order to ordering it. The same thing I did. So after that, I will plot using this function, interaction plot, but since interaction plot, in order to use this, is I should attach the data frame here, FRCBD, and I use the interaction plot function, and then I will give the X factor, means that will be the X level, and then the trust factor is the one that will be going in the graph, and then the response variable will be, for example, in this case, plant height. So, and then how he calculate for you, the function is mean, in this case. So he will calculate the mean of the plant height for each factor for nitrogen and irrigation, and then he plot for us the interaction plot. So if we run this command, you will get it, the graph like this. So in this case, as you see, there is some interaction level when we see from the medium to the high, there is interaction. Otherwise, for the case of low, medium nitrogen level with irrigation, we don't have any interaction. So this one shows a strong crossover interaction between the medium and the high level of nitrogen over the irrigation, but the medium and the low level of nitrogen with irrigation doesn't have crossover interaction. Instead, they have interaction, but it's not crossover. It means we will not have any change in no change in rank in this case. Okay. So after that, the next step will be, in order to analyze the factorial analysis, to define the mathematical model. This mathematical model is the one that directs us in order to fit the model using our R function. So in this case, as it is a factorial RCBD design, our mathematical model is defined like this: Yijk equals the mean value plus the block effect plus the factor 1 effect plus the factor 2 effect and plus the interaction, and finally we'll have the error associated with the observed value. So based on this, we can finally use to design our fitting model in the our analysis. The next step is also here is, in order to analyze, is to define the trait of interest to be analyzed. In this case, we have yield, plant height, protein content. So we learn this, and then for the coming analysis, we'll have different functions necessary, different packages. So we should load this package. The first one is table. This table is helpful to create a new or an empty table or a type of table that can be used to store our outputs. The second one is mean, AMM mean. This one will help us to do the LS mean or the AMM means to compare treatments or factors. This is multi-comp view is a package using for multiple comparison, and also multi-comp also used in order to display the letters on the mean comparison. So multi-comp will use servers like that. And finally, DPLYR dplyr is helpful in order to data wrangling. Okay, so after that, we need to create the table that is going to be used to store our output, possible output. The first is ANOVA table. The second one will be the mean table for the first factor. The third one, the mean table for second factor, and the mean table for the interaction. So in this case, since you are interested to analyze multiple traits, that is in this case 3 traits, so we should create a loop that's called a for loop that can be used in order to iterate our analysis through each trait. So in this case, we use here, as you show it, we select a trait from each trait. From traits, we select a trait, and then we will evaluate this trait using this function, this expression. So this linear model expression will be executed every time when we select a trait. So as you see it, this trait will be substituted when you sample one trait from these traits, and then he analyze and then go to the next and until the last trait in the within a traits. So this is the evaluation function. This one parse and this text will be paste this expression within the quotation mark. And then after this, the output is saved with AVF. And then this AVF will be extract the ANOVA table using the ANOVA function, and we change as a data frame and we'll save it as AV table. And then from this, in order to not lost which ANOVA is for which trait, we will create additional trait column, and we'll paste the trait we subsetted every time to that column. And then finally, we will add additional column in the table. That is, the column name is called source of variation using this add column function that's obtained from the dplyr package. So we will add this column before the degree of freedom in the ANOVA table. And finally, since once already we did source of variation added in the ANOVA table, we don't need the row name, so we will use the row name ANOVA table and none, so we will remove the row name in this case. And then finally, we will store this one using the ANOVA on the ANOVA table we created here, the table we created here. So he will store automatically when each trait evaluated each time, the ANOVA table of each trait will be saved, combined together in this ANOVA table. The same is true for the mean separation test. For the mean separation test, we use LS means. So for the LS means, we will provide ANOVA AVF factor, the analysis of ANOVA output, and then we give the factor to be compared. So in this case, nitrogen, factor 1. And the second one will have irrigation. And on the third condition, we'll have the interaction of nitrogen with irrigation. So in order to identify for which trait is this mean is accounted for, we will add additional column called traits. So we'll add for both of them. This LED function will help us in order to show the letter display. If there is significance difference, he will show different letters or numbers in this case, or if there are no significant difference with each other, will show you the same number. But this one is show you the letter on each significance difference levels. Finally, we will combine all the analysis output of each trait using this mean table factor 1, mean table factor 2, and then for the interaction, mean table factor 1 and factor 2. So after this, for example, now we can run the analysis. This is over done. So if you look for the ANOVA table, for example, here, he will show you like this, that your table will be like this. We have source of variation, block, nitrogen, irrigation, nitrogen with irrigation interaction, and then residual. In this case, yield didn't have any significance difference. When you go to for the probability of F, we don't have any significance differences. The second one is plant height have significance difference, and is a significance difference is observed only for nitrogen, and some level of and also for the interaction with nitrogen and irrigation. So this interaction, as you see it, here is a plant height, so it shows that there is some interaction here, a crossover interaction between the medium level and the high level. So that is an interaction. Even this one, the performance is also, as you see it, the difference, even if there is no any crossover interaction, but there is some level of interaction, since when you see from medium to high, for example, this medium and the low value of nitrogen, as you see, from medium part it will be too narrow, but if it go to high irrigation, the difference will be high. So that shows some level of interaction, but it's not a crossover type. Okay, so finally, what we're gonna do is, after we generated our output, the last part should be to save this output to our computer. So that can be done using the package called OpenXLX. These are functions that help us to save our outputs. So before we save it, we should collect all our output into a single list file, in this case called out. So we list ANOVA table. As ANOVA table, we give the name ANOVA table. For mean fertilizer, we use mean table factor 1 as mean fertilizer. Mean irrigation, mean table factor 2 will be named as mean irrigation in the XL sheet. Mean factor 1, factor 2, and it's named as mean interaction. So this ANOVA table, mean fertilizer, mean irrigation, and mean interaction will be the sheet name in the Excel file. So here we will save using the right XLSX function. We provide this output here, and then we will give the new name that will be saved in our file, like this Factorial RCBD XLSX. Don't forget the extension XLSX. Overwrite true means if you have another file with the same name, he will overwrite over it. So now we will run like this, and then we'll run over it. So if we go to our file, we'll see that summary with Factorial RCBD XLSX is created and our output saved there. So we can, after that, you can go there and do our writing. So this is how to analyze RCBD factorial with two factors. So in the next one, I will show you in the next video. I will show you how to analyze factorial with a Latin square design. Thank you very much for your attention. If you have some question and suggestion, you can provide on the comments. Thank you.